Hi, my name is Chris Harris. This is my presentation on the electronics and acoustics of digital synthesis. This is my first slide, and it is the title. My next slide. What is a digital synthesizer? A digital synthesizer is a synthesizer that uses digital signal chain processing, which is also known as DSP. These techniques, which are used to make musical sounds out of oscillators which replicate sound waves. You have many different types of sound waves. You have pulse, or you have triangle, square, etc. And these digital synthesizers produce those sounds. Obviously, because they're digital, they're written in software. They're not analog, they're not actually mechanic, so there's a lot of things that are involved with making these synthesizers. First of all, one of the main things that is used to make them is programming. A digital synthesizer has the same functions as a modular analog synthesizer, as I mentioned. And this is done because instead of circuitry, each module is represented by a subroutine within the main synthesis program. This program essentially is a loop that repeats once for each output sample. The subroutines must each be executed at least once per period sample period. And many of them must execute once per note per sample period. Thus, the number of notes that may be played and the complexity of the sound available is determined by the speed of the CPU. That is obviously processing power and everything relating to your computer, so the actual programs can only work as well as your computer can work, essentially. As I've mentioned here, with personal computers, the fastest the CPU are the most expensive, and this is reflected in the cost of the instrument as well. So some people make lower quality instruments and sounds, so they're cheaper, as well as computer companies also making cheaper computers. This is the Next, I'm going to show you is a typical signal flow, the digital equivalent of a patch, and basically the routing and stuff of how it works. This is a diagram, so you can get an idea of how it works. As you can see, this is my example. First, you start down here with MIDI controllers. So you've got your MIDI keyboard or your mouse as your initiator. And that goes to signal generation, voice level controls, and instrument level controls. They all simultaneously go through at once. Next, from signal generation is voice level processing, and following that is instrument level processing. How they route through, and then this last one, instrument level processing, is basically your volume, your amplitude of how loud it comes out, and you can generally alternate that in the synthesis. Signal generation wavetables. The heart of any signal generation routine is the wavetable. A wavetable is a section of memory that contains and represents a segment of sound. This may be as simple as a single cycle of sine waves, or maybe a complete recording of a traditional instrument being played on a note. An example of that would be Contact. It's a sampler, and you can play real samples that are actually recorded. And then you have other synthesis, such as Massive, which is a wavetable synthesizer. It has many different types of wavelengths. But it's actually an additive synthesizer that has many different wavelengths. How this works is then this may be as simple as like a single cycle of sine waves on one oscillator, just producing one sound, or this can be a complete recording of a traditional instrument. On each sample period, a value is taken from the wavetable and sent to the output. If the sample rate of the synthesizer is the same that is used for the initial recording, the pitch should be produced. The pitch produced will be the same. In this case, a single cycle wavetable, the frequency produced will be the sample rate divided by the number of entries in that table. To produce a continuous tone, the table is read over and read over again on a constant loop. So when you press a keyboard with your MIDI controller and you get that initial sound of the saw wave going it's on constant loop being repeated. To play over pitches, the values in the table are taken out of order, and every other value is output. The frequency is doubled. To go down an octave, or each value could be used twice, and that would distort the wave noticeably, which wouldn't sound great, so you wouldn't want that. Modern instruments calculate a value that would fall between the entries in a table, a process called interpolation. Sophisticated interpolation routines can produce any pitch desired, including smooth, glissandi, and pitch bends, which is making the sound extremely go up and down without it losing its complex sound to its frequencies. Interpolation is the most time-consuming process within the program loop, so the numbers of tones you can play this way is going to be limited in a particular instrument. This will then determine the maximum number of notes possible, depending on how many tones are used to create a note. Variation of tone, as we said in the last sentence, it's quite complex to get these, and this is basically going to explain how you can do that. Wavetable synthesis has one serious drawback, a very static spectrum of the sound. Most real instruments produce a dynamic spectra that can change over duration of a note and never repeat in quite the same way. Simple wavetables give us the sound of a toy organ, occasionally useful but basically boring. To get this, a variety of strategies can be found. There are many different synthesizers these days that actually use real samples, and another way that they use it is using a complex modelling design, which is a whole new thing, but I'm going to mention that later in my presentation on what modelling is. Large wavetable lengths. Said that wrong. Large wavelength tables. Essentially, there's enough sound in the wavetable to play an entire note on one pass, or at least on loop, with a moderately long period of sounds like vibrato. Most often, these class of synthesizers use recordings of traditional instruments as the wavetable content. You may be limited to a particular set of recordings, or you may be able to make your own. These are the ambiguous samplers and sample playback units. Sampling was first marketed by EMU, and they have a wide range of instruments based upon the technique, but nearly every instrument on the market today has some recorded samples in it. Here is an example of one of these large wavetable synths, massive. You have here 3 different oscillators that have a choice of each oscillator to something silly like 27 different waveforms. Half of them are natural sounding. You get your typical sine waves and triangle waves, and you also get pulse waves. You also get these kind of hybrid like replications of analog sounds that they try to recreate digitally. And they also have these new sounds that are made that aren't humanly possible to do with our voices, or instruments yet haven't been created to make certain sounds sound this way. And this is Native Instruments' massive version 1.5. I've explained enough already now about what these synths can do. I've explained some of the science and some of the programming behind it as well. I'm now going to explain a bit more in depth what actually produces the sound, what the single unit that initially starts the sound is. And these are oscillators. Oscillators produce the original sound which you can hear in your patches, which is then fed through the rest of the signal path in the synthesizer. Oscillation itself is the production of a certain type of waveform, which produces a different sound depending on the shape of the waveform. The waveform is constantly run depending on the speed/pitch of the note. So if an oscillator is set to a low enough pitch, you eventually hit gaps due to the slow speed of the oscillation. common oscillator waveforms